Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Fugacity from Volumetric Data. In the previous lecture we have seen how to estimate thermodynamic properties if volumetric information or volumetric measurements are available, right. So, this lecture is a bit continuation of a previous lecture. So, what we do, we have a kind of recapitulation of previous lecture. We have seen primarily how to estimate thermodynamics properties like U, V, S, H, A, G, etc. provided if you know V as function of temperature, pressure and composition, or as temperature and pressure are independent variables. Under such conditions, if you know the volumetric information, then how to estimate the thermodynamic properties, those things we have seen. In addition to that one, we have also seen how to estimate fugacity of a component in a mixture if we know the volumetric data information in the form of a volume explicit form, that is V as function of temperature, pressure and composition, or otherwise if we know the volumetric data and then if you have a temperature and pressure as independent variables, then how to measure thermodynamic properties, those things we have seen. And then in addition to that one, we have also seen how to estimate fugacity coefficient for non-ideal systems. Non-ideal system, how to estimate the fugacity coefficient or fugacity for a component in a mixture or a pure component, that we have seen as temperature and pressure as independent variables, right. And then we derived for a component I in the mixture, fugacity coefficient can be estimated using this expression, that is RT ln phi is equals to integral 0 to p Vi bar minus RT by p dp. So, whatever the volumetric data information is available in volume explicit form, that we obtain the partial molar volume of ith component for which we wanted to measure the fugacity, and then substitute here, do the simplification. So, then we get a fugacity coefficient of that ith component in the mixture. So, we have also taken an example of van der Waals equation, and then we derived what is the fugacity coefficient phi I for a component I in a mixture of gases which obey van der Waals equations of state. Then for a pure component also we have derived these relations, that is RT ln Fi by P pure I is equals to integral 0 to P Vi minus RT by P dP. Here simply we are having Vi in case of pure component, because for pure component partial molar volume is nothing but its molar value, right. Then also we have derived this Levy's fugacity rule, right, which is true when when we mix the component such a way that there is no change in total volume. Fugacity of component I in the mixture you can know directly without doing any calculation if you know fugacity of the same component as if it is a pure component, simply by multiplying the volume fraction of that particular component in the mixture, you will get a fugacity of that particular component in the mixture, that is Fi is equals to Yi F pure I. Fi is nothing but fugacity of a component I in the mixture, F pure I is nothing but fugacity of that same ith component, but as a kind of a pure state, it is not mixed with anything. So, this derivation we have seen, and then also for fugacity of a pure condensed phase we have derived this relation, Fic is equals to Pis Pis exponential integral Vic by RT dP, integration from Pis to P. Pis is nothing but the saturation pressure. Below the saturation pressure, vapor form is there, and then beyond the saturation pressure the condensed liquid form may be there, right. So, then at the saturation pressure these two phases would be at equilibrium, right. Pis is nothing but the fugacity of that particular pure component, but under the saturation vapor conditions, okay, or Pis is nothing but the fugacity of a saturated vapor. And then if we have made an assumption that if the conditions are the pressure change is at delta P is far away from the critical range, or saturation pressure etc. are far away from the critical conditions of the system, then we can say that Vic, that is the molar volume of the condensed phase, is independent of the pressure, or the condensed phase is incompressible. Then we can simply integrate this one as Vic as independent of pressure, and then we have this exponential correction, exponential Vic P minus Pis by RT, and this we named it as this particular thing we call it as Poynting corrections. And we have also seen how much important it is. It depends on what is delta P. Delta P is nothing but P minus PIS. P is beyond the saturation pressure, then only there will be a kind of condensed bed. If the P is below the saturation pressure at that given temperature, then we will not be having a kind of condensed phase, we will be having a saturated vapor kind of thing. Okay. So, depending on the magnitude of this delta P, we can say how much important is this Figastic correction. We have seen, let us say if VIC is approximately 100 cc per mole, then we can say this if delta P is less than 10 bar, this Poynting correction is almost negligible. That is what we have already seen. Then for a binary mixture obeying van der Waals equation of state, then we have found this Figastic coefficient of first component phi1 as this one, this is what we have derived, and then for pure component obeying same van der Waals equation we have derived this relation, and then we made a kind of connection between these two equations, and then we have written like this equation F1 is equals to Y1 F pure 1 and then multiplied by this exponential factor. This exponential factor is coming additional as a kind of correction to the Lewis-Figastic rule. If you recollect, Fi is equals to Yi F pure I is nothing but the Lewis-Figastic rule, and there is a correction here. This is what we have seen in our previous lecture. Now what we do, we take a few example problems based on what we have seen the Figastic calculations etc. from volumetric information. If temperature and pressure are as kind of independent variables, those things are we have derived, right. Based on those things, now we see a few example problems. Example 1, assume that the equation of state of pure gas is PV is equals to RT plus B minus A by RT P, where A and B are constants. Derive an expression for Figastic of pure gas. Actually this is nothing but the van der Waals equation that we have already seen in the previous case, and then these A and B are a kind of a van der Waals constants, right. We have derived F pure 1 by substituting in F1 y tends to 0. Like what we have done, we have got F1 expression for a van der Waals equation, and then we substituted y2 tends to 0. Actually if you remember, this is having two corrections, two exponential corrections. Second correction is having y2 term, so that y2 term goes off, and then only first exponential term we have. So then what we got, F pure 1 is nothing but P exponential of B minus A by RT, this is P by RT, this is what we have derived, right. This we derived by substituting here in this expression y tends to y2 tends to 0 or y2 is equals to 0, that we substitute, we got it. But let us say if you do not have this F1 relation, then how do you get F pure 1, right. So that is what simply we are taking on a kind of a starting example problem for simplicity as well as cross checking. This equation of state we have to write in volume explicit form. So when you write it, we have RT by P plus B minus A by RT as V, and then for pure component we have already derived this relation that RT ln F by P pure I is nothing but integral 0 to P V minus RT by P. So simply here in place of V you substitute in place of V you substitute RT by P plus B minus A by RT, then we have this thing. So RT by P, RT by P cancelled out, so then we have B minus A by RT P, this is what we have. So then ln F by P pure I is equals to B minus A by RT P by RT, this left hand side whatever RT is there we are bringing into the right hand side. Then F pure I is nothing but P exponential B minus A by RT P by RT, and this is same expression as the one that we have derived from F1. In F1 relation that we derived in previous class for van der Waals equation, a binary mixture obeying van der Waals equation of state that we have considered, and then we have derived F1 relation. In F1 relation by substituting y2 tends to 0, then since it is a binary mixture, if y2 tends to 0 then it is a pure 1. So then for that case F pure 1 we derived like this, and then let us say the pure we do not know what is the F1 for a binary mixture. Then pure from the pure expression for pure gas whatever the Figastic expression is there, that we made use, and then we got the same thing. So that a kind of practice as well as a cross check. Now we take another example problem. Consider a pure liquid acetone at 100 bar and 382 Kelvin. At this temperature, this saturation pressure is 4.64 bar. The Figasty coefficient of saturated vapor, that is FIS, is nothing but 0.904, and then molar volume of the liquid, that is condensed phase VIC, is nothing but 73.4 cc per mole. What is the Figasty of pure liquid acetone if the molar volume does not change with pressure? The pure acetone is in the liquid form, that is in the pure condensed form, right. That means then whatever the Figasty relation that we have developed for pure condensed phase, that we have to use. Okay. So before solving the problem, let's just list out what has been given. Temperature is given, pressure is given, saturation pressure is given. That means delta P, that is P minus PIS, is given. Figasty coefficient of saturated vapor is given, FIS. So that is given. Molar volume of the condensed phase, VIC, is given. So simply substitute them in this equation that we have derived in previous lecture. VIC is independent of the pressure difference, and then we can say that it is kind of incompressible condensed phase. So then we can integrate this this particular part without worrying whether VIC is dependent on the pressure or not, because we have seen that it is independent of a pressure for incompressible phase. Then we get VIC by RT delta P. So that is what we have. Substitute all these quantities because everything is known. Then we get Figasty of condensed phase, and that is pure acetone, is nothing but 5.23 bar. Okay. Since it is a kind of pure acetone, at these conditions it is pure acetone is in the liquid form. So then that is beyond the saturation pressure. So obviously as a cross check, what you can see whether the Figasty is coming beyond the saturation pressure value or not. If you are getting the value FIC below the or equal to the PIS, then that means you are making some mistakes in the calculations, because it's a pure acetone is in the condensed form, and then so obviously it's Figasty, which is nothing but the corrector pressure, that should be beyond the saturation vapor pressure, that is beyond 4.64 bar. So then we are getting higher than that value. Okay. Then another example problem, consider a mixture of M gases and assume that the Lewis-Figasty rule is valid, that is capital V is equals to sigma Ni Vi, or Fi is equals to Yi F pure I, that is also known. So Fi is equals to Yi F pure I. This is what the Lewis-Figasty rule in terms of Figasty. Okay. Whereas this capital V is equals to sigma Ni, small vi is nothing but Avogadro's law. So for this case, show that the Figasty of mixture F mixture is given by capital pi I is equals to 1 to m F pure I power Yi. This is what we have to prove, right. And then here this capital pi is nothing but a product, like sigma we take for the summation. Now here in this case, this capital pi is for the product. So where here in this expression Yi is nothing but the mole fraction of component I, and then F pure I is the Figasty of pure component I at the temperature and pressure of the mixture. This is what we have to prove. So but what we have, Lewis-Figasty rule is nothing but Fi is equals to Yi F pure I. This we will be using somewhere later stage, right. Let us make note of it and then keep it here as it is. Gibbs energy of a mixture can be related to partial molar Gibbs energy as G minus G naught, or capital G minus capital G naught, is equals to sigma Yi small gi bar minus small gi bar naught. So small letters we are using for the molar properties, and then bar is for the partial molar properties. Okay. And then capital letters we are using for the total properties. That is what symbols we are following for this lecture. In the previous lecture also we followed the same thing. So now what we have to do, we have to make a relation what is G minus G naught for a mixture in terms of Figasty. Similarly, we have to make a relation what is Gi bar minus Gi naught bar for a ith component in the mixture. Substitute them here, simplify, then you will get the relation. And it is quite straightforward and simple, because we know dg is nothing but RT dln F. If you apply this expression for a mixture, then we will have G minus G naught is nothing but dg, and then RT ln F mixture minus RT ln F mixture naught. This naught is a reference state. Okay, reference state. At reference state or some reference standard temperature pressure that we take as a kind of reference state, because we calculate these things with respect to some relative to some reference state. Okay, G naught is nothing but Gibbs energy at that reference state. So we take reference state as a ideal gas, and then if the mixture is ideal, if the gaseous mixture is a kind of ideal gas, then fugacity of that mixture should be total pressure simply. Okay. Then we get here RT ln P, right. So now the same expression now here, so the in this part this is known. So now similarly we apply dg is equals to RT d ln F expression for the Gi bar minus Gi naught bar. Okay. When you apply this one, dgi bar is equals to RT d ln Fi, right. So then for the ith component in the mixture, Gi bar minus Gi bar naught is equals to RT ln Fi minus RT ln Fi naught. Now ith component we are writing, we are not writing for the mixture. So that is the reason Fi naught are there. And then for one equation we cannot have two different reference states. So here also we have to take a reference state as a kind of ideal gas at low pressure and then certain temperature T, and then if that is the case, then for ideal gas mixture fugacity of ith component in the mixture is nothing but the partial pressure of that component. So that means Fi naught is nothing but Yip. So that we substitute here. So now we know G minus G naught, we know Gi bar minus Gi bar naught also we know. So we can substitute them in this equation and then simplify. So this is what we have, RT ln F mixture minus RT ln P is equals to sigma Yi Gi bar minus Gi bar naught. That means this Gi bar minus Gi bar naught is nothing but RT ln Fi, this one, and then minus RT ln Yip, right. But this Gi bar minus Gi bar naught is multiplied by Yi. So then these both the terms ln Fi ln Yip should be multiplied by Yi, and then there should be a summation. Okay. And then RT that we have taken common, and then RT we are taking common. Now this part what we do, we add RT sigma Yi ln Y, and then we subtract same quantity RT sigma Yi ln Y. RTs we have taken outside as a common, just for simplicity. Okay. Simplicity as well, we have a relation that Fi by Yip kind of things we need actually. Okay. So then now what we do, next step we combine these two terms, and then we combine remaining these two terms. Then what we get? Then we get ln F mixture minus ln P is equals to sigma Yi by sigma Yi ln Fi by Yi, and then remaining one is minus sigma Yi ln Yip by Yi. So Yi cancelled out, so ln P we are getting this one from the remaining two terms, and then RT anyway we can cancel out. So after rearrangement, combining this in the right hand side, first and third term when we combine, we get ln Fi by Yi, and then when you combine the second and fourth term of right hand side, you will get ln P simply, or ln Yi by Yip minus ln Yi is nothing but ln Yip by Yi, and then Yi is cancelled out. So then ln P would be there, and these terms anyway are carrying sigma Yi and then sigma Yi both the terms. So that is the reason we have sigma Yi ln Fi by Yi minus sigma Yi ln P. Now what is this? Sigma Yi ln P is nothing but simply ln P, right. So sigma Yi ln P is nothing but ln P sigma Yi is nothing but 1. So it is ln P. That means ln F mixture minus ln P is equals to sigma Yi ln Fi by Yi minus ln P. So this ln P can be cancelled out from either side. Then we have this expression ln f mixture is equals to sigma yi ln fy by yi, but this is not the final solution. However, it is important part. Now, in this equation if you substitute Lewis-Figasti rule, because till now till obtaining this point we have not applied Lewis-Figasti rule. So, when we apply Lewis-Figasti rule in this equation, right, then what we have, we can simplify that equation further to get the required answer. So, Lewis-Figasti rule is nothing but Fi is equals to yi f pure I, that if you substitute in this equation which we just derived. So, in place of Fi I am just writing yi f pure I. So, yi is cancelled out. So, ln f mixture is equals to sigma yi ln f pure I. This if you say, let us say, first you take off the ln, so that in the right hand side we get the exponential and then left hand side we have f mixture. So, f mixture is nothing but exponential of y1 ln f pure 1 plus y2 ln f pure 2 and so depending on the number of components. yi whatever is there before ln f pure I, that we take inside the ln part, so that we get ln f pure I power yi. So, that is ln f pure 1 power y1 plus ln f pure 2 power y2 and so on. Right. So, now we write this one exponential of a plus b as exponential a exponential b form. So, then we have this form, right. So, now so that exponential ln for each term may be striken off, so that we have f pure 1 power y1 f pure 2 power y2 and so on, so like that, it is a product. So, that is f mixture is nothing but pi f pure I power yi, and then this product capital Pi is from I is equals to 1 to m, because m number of components are there, hence it is proved. Another example problem, a binary gas mixture contains 25 mole percent of A and 75 mole percent of B at P is equals to 50 bar and T is equals to 100 degree centigrade. The Figasti coefficients, that is phi A, phi B, are given as 0.65 and 0.9 respectively. What is the Figasti of the gaseous mixture? So, Figasti of the gaseous mixture is required, that is F mixture is required, okay, but this phi A, phi B are given, or Fa, Fb are given, because P as well as the Ya, Yb are also given on mole basis, right. So, individual F's are given, but for the mixture we have to find out. So, just in the previous solution, in the previous example problem number 3, we have derived that ln f mixture is equals to sigma yi ln fi by yi. So, till deriving this part we have not made use of any assumption whether the mixture is obeying Lewis-Figasti rule or not. And then now in the fourth example it is not given whether Lewis-Figasti rule is obeyed or not. So, we cannot take that Lewis-Figasti rule validity as we have taken in the previous case, because it is not given for this problem, it is given only for third problem. So, up to this part in this fourth problem, up to this part derivation is same as in the previous problem. From this part onwards, the third example different derivation is there, but we need up to this point. So, since we have already done, I am not redoing it. Okay. Now, since nothing is given whether this mixture obeys the Lewis-Figasti rule of the mixture or not, thus consideration of the Figasti coefficient or thus consideration of the Figasti Fi as phi yip is more appropriate. So, in this equation ln f mixture sigma yi ln Fi, in place of Fi I am writing phi yip divided by yi. So, this yi is cancelled out. So, that means sigma yi ln pi I sigma yi ln phi p. So, this I can write for a binary mixture, because it is a binary mixture, like this I can write it. Then what I can do, ln phi a p I can write ln phi a plus ln p. Similarly, for the second one also I can write similarly like this. Now, I can separate these two terms, ln ya ln phi a plus yb ln phi b as one term, and then remaining two terms ya plus yb multiplied by ln p. So, this is nothing but 1. So, when you take off the logarithmic, or without taking of the logarithmic also you can substitute what is ya given, what is yb given, and what is pi a, what is phi a given, what is phi b is given, and then p is also given. So, substitute directly and then get the F mixture value. Okay. So, then that comes out to be 41.5 hours. Okay. Now, what we do next, we see how to estimate thermodynamic properties with temperature and volume as independent variables, because in the previous lecture we have seen, we have discussed, most of the volumetric data is available as a pressure explicit rather than the volume explicit. In the previous class we estimated thermodynamics properties from equations of state, if that is available as a volume explicit form, but mostly these equations of state are available as a kind of a pressure explicit form, right, that is temperature and volume has to be independent variables. Okay. So, under such conditions how to estimate thermodynamics properties? Again what we can start with? We can start with the Maxwell relations. From the Maxwell relations any two thermodynamics properties can be estimated easily. Once two thermodynamics properties estimated, so the rest other thermodynamic properties can be estimated, right. Since the volumetric properties of fluids are usually expressed by equations of state that are pressure explicit, it is more convenient to calculate thermodynamic properties in terms of independent variables T and V. At constant temperature and composition, one can use following Maxwell's relations to find the effect of volume on energy and entropy. Previous lecture what we have seen, effect of pressure on entropy and enthalpy, right, because in the previous lecture we have written as a kind of volume explicit form. So, there we can see the effect of pressure on the total entropy and enthalpy. Once the entropy and enthalpy we calculated, the rest of the all other thermodynamic energies that we have calculated. But here in this case it is a pressure explicit form. So, we are going to see effect of volume on energy and entropy, that is internal energy and entropy. Once this U and S are known, H, A, G etc. we can calculate. So, this is one of the Maxwell relations. So, but we are taking constant temperature. So, du is equals to T dou P by dou T at constant V comma Nt minus P dV, that is what we are having. Similarly, ds is equals to Cv by T dt plus dou P by dou T at constant V Nt, but it is again we are doing these calculations at constant temperature and composition. So, dt is 0. So, ds is equals to dou P by dou T at constant V comma Nt. So, now if you integrate these equations you can get the energy of the system and then entropy of the system. Once these two are known, rest all other things we can easily calculate, as we have these relations, several relations like H is equals to U plus PV, A is equals to U minus Ts, G is equals to U plus PV minus Ts, and then chemical potential. So, when defining chemical potential as a function of Helmholtz energy as dou A by dou Ni, Tv are kept constant along with the engine. And then this RT dln Fi is nothing but delta mu I, that is mu I minus mu I naught, and then Fi naught we are taking as a kind of reference 1 bar. Molar energy of pure I as an ideal gas at temperature T is given by Ui naught is equals to Hi naught minus RT. So, that is once you know the internal energy U and then entropy, you can calculate all these properties without any difficulty. But our aim is what is this fugacity of ith component in the mixture, or what is the fugacity of pure component I. This is our interest, right. So, now we try to do something how to get this information as keeping temperature and volume as independent variables. Fugacity coefficient from volumetric data information in the pressure explicit form. This is important. Previous one is the volume explicit form. In the pressure explicit form, that is P as function of T, V, N1, N2 and so on are known, or as temperature and volume are independent variables, then what is the fugacity coefficient phi I? That is what we are doing. So, we have a relation dg I bar is equals to RT dln Fi, and then that is nothing but Vi bar dP. This is also we have seen one of the previous lecture, right. So, now this equation if you partially differentiate with respect to pressure, then we get dou Gi bar by dou P at constant temperature and composition is nothing but Vi bar, and that is nothing but RT dou by dou P of ln Fi at constant temperature and composition, right. So, but anyway we do not need this third part, we need only this part, okay. But what is Gi bar? Gi bar is nothing but dou G by dou Ni at constant temperature, pressure and then Nj. And then what is this dou G by dou Ni at constant temperature, pressure and Nj is nothing but mu I, right. So, that means dou Gi bar by dou P, I can write it as a dou mu I by dou P. So, the same thing I have written like this, okay. And this dou mu I by dou P I am writing in different, because now I cannot know effect of pressure, because I can know effect of volume only here, because temperature and volume are independent variables, and out of these two temperature I am keeping constant. So, effect of volume I can find out, but effect of pressure I cannot find out for in this case. So, then what I do, I write this one as dou mu I by dou V multiplied by dou V by dou P like this, okay. So, that means here in place of this RT dou ln Fi by dou P is nothing but this particular thing now, fine. By combining these two equation, what we get, RT dou ln Fi by dou P at constant temperature and composition is nothing but dou mu I by dou V multiplied by dou V by dou P. But our interest is Fi, okay. What is dou V by dou P we do not know, we can find out somehow, let us see. And then what is mu I, unless we know what is mu I, we cannot further move forward. So, that means we have to find out what is dou mu I by dou V now, that is what we try to do it now, right. So, before doing what we do, whatever dou V by dou P in the right hand side is there, that I take it to the left hand side as dou P by dou V, so that I can write this left hand side part as RT dou ln Fi by dou V kind of thing, right. Because now I wanted to know the effect of volume on fugacity. If you change the volume, then how the fugacity is changing, because temperature and volume are independent variables, and then temperature we are fixing constant. So, by changing V, how Phi or Fi is changing, that we have to find out. So, RT dou ln Fi by dou V is nothing but dou mu I by dou V. So, now I have to find out this one. If I find out this one, I can substitute here, I can find out the Fi. Once Fi is known, Phi is straightforward. We have A as function of temperature, volume and composition, but at constant temperature, what we can write here? At constant temperature, dou square A by dou V dou Ni is equals to dou square A by dou Ni dou V, I can write it at constant temperature. This one I can write dou by dou V of dou A by dou Ni at constant Tv Nj is equals to, and then this part I can write dou by dou Ni of dou A by dou V, right. So, now if I find what is dou A by dou Ni and dou A by dou V, I can substitute here and then see how I can simplify or relate it to the chemical potential. We have equation that dA is equals to minus S dt minus P dV plus sigma mu I dNi. Now, this one at constant temperature, volume and Nj, if you partially differentiate this equation, then dou A by dou Ni, with respect to Ni, if you partially differentiate this expression by keeping temperature, volume and moles other than Ni as constant, that is Nj as constant, then dou A by dou Ni is nothing but simply mu I. And then similarly at constant temperature and then constant composition, that is what we are doing. Then under such conditions, if you partially differentiate this equation with respect to volume, then dou A by dou V by keeping constant temperature and Ni as a constant, then we get that should be equals to minus P, that should be equals to minus P from this equation, right. So, this equation also we have derived in one of the previous lecture. So, now here dou by dou Ni I can write as a kind of mu I, and then here dou A by dou V I can write it as minus P here. When I write it, I will get dou by dou V of mu I is equals to minus dou by dou Ni of P. So, I want this dou mu I by dou V something in terms of measurable property, so that I can easily do, because I do not know any information about mu I. Okay, it is not measurable. Okay, so non measurable mu I is now related to the measurable pressure, the change in pressure with respect to change in the composition by keeping constant temperature, volume and Nj. So, this is now this I can substitute here, equation number 49. Okay. Then what we have RT dou ln Fi by dou V in the left hand side of equation 49 as it is. In the right hand side what we have dou mu I by dou V. So, in place of dou mu I by dou V I can write minus dou P by dou Ni, right. So, let us keep this equation as it is without doing any correction, but now what we do, we take RT dou ln PV by dou V and then expand it. If we expand it, RT dou ln P by dou V plus RT dou ln V by dou V, that I can write, right. So, this part RT dou ln V by dou V is nothing but RT by V. Why I am writing? Because I want something like Fi by Yip terms or F by P terms, and then as of now there is no P term here. Unless that comes into the picture, I cannot define a Figastic coefficient. I can have a relation for the Figastic, but not for the Figastic coefficient. Okay. For that reason this arrangement is there. Okay. So, RT dou ln PV by dou V is nothing but simply RT dou ln P by dou V plus RT by V. Now, what I do? I write this part minus RT, this part whatever first term in the right hand side, that I take to the left hand side. So, that is minus RT dou ln P by dou V, and then right hand side term RT by V is as it is. This remaining term minus RT dou ln PV by dou V, that I have written in the right hand side of the equation number 52. Now, simply add these two equations 51 and 52. Then you will have this RT dou by dou V ln Fi and minus RT dou by dou V ln P. I can write RT dou by dou V ln F pi by P. Ln A minus ln B is equals to ln A by B form, and then we are integrating. Okay, that is left hand side is done. Right hand side, what are the terms we are having? We are having RT by V minus RT dou ln PV by dou V, and then minus dou P by dou Na terms we are integrating. Now, coming to the integration limits, we are taking V is equals to infinity to certain V value, right. Why it is? Because we cannot start with 0, V is equals to 0, because we cannot, any system that you take, it will have some volume. So, 0 volume, that means system is not existing, that we cannot do, right. But the other side, if you see V is equals to infinity, in the sense it is a large volume, infinite volume, and then particles, if the volume is infinite, then fluid particles or whatever the gas particles are there, they will be away from each other. Then under such conditions, if V tends to infinity, that gas is obviously ideal gas behavior kind of thing. So, from ideal gas behavior, that will, this V infinity, V is equals to infinity will serve two purpose, as a kind of lower limit of the integration, and then as V decreases, the non-ideality will come into the picture. So, that other limit V will be taken as a kind of upper limit. So, either way it is applicable as a kind of lower limit for the integration, as well as to take the bring the reference, because all these calculations wherever the corrected pressure, the fugacity etc., that we started defining by taking the kind of ideal gas as a kind of reference. From the Gibbs-Duhem equation we have taken, you know, whatever the constant temperature and then pressure, mu y is nothing but, you know, that is S dt minus P dV plus sigma mu I dNi is equals to 0. In that case, we have taken from there, by taking constant temperature pressure, I defined, you know, this dou mu I by dou Ni is nothing but the G kind of thing, those kind of things we have done, and then we brought it. That is the That is basically the corrected pressure concept, or the fugacity is nothing but corrected pressure concept, right. That concept has come as evolved from the limitation of ideal gas, right. If the gas is obeying the ideal behavior, then fugacity of the mixture should be equal to the total pressure, that is one limitation. And then let us say if it is mixture of the gases, and then for the fugacity of ith component in the mixture should be equal to the partial pressure of that component in the ideal gas mixture. That is the basis limiting condition that we have taken. That is the reason we have to take this V infinity as a kind of reference, right. In the previous case where we have written volume explicit form derivations, where there we have taken P is equals to 0 as a kind of lower limit. Why? Because there also when P is equals to 0 or P tends to 0, we can say that system reduces to the ideal gas behavior, right. So, that is the reason here we have taken the limits V infinity to V, not from 0 to V. Okay. Now, when you simply integrate this one, RT ln f pi by p we will get here, okay, because this dv is cancelled out, and then f pi by p at certain volume we do not know. So, we are estimating it, okay, or we are developing an expression that is as it is, and then lower limit is RT ln f pi by p at v is equals to infinity. At v is equals to infinity, what is f pi by p, that we have to find out, okay. And then now here what is v we do not know, what is dou p by dou ni we do not know. So, we cannot integrate these two terms. So, then what we write? We write integral v is equals to infinity to v RT by v minus dou p by dou ni as it is, and then this part if you integrate you will get RT ln PV, simply RT ln PV, because RT dou by dou V ln PV and then dV with respect to dV we are doing integration. So, that is d ln PV. So, ln PV d integral of d ln PV is simply ln PV. So, there are two limits, one is the RT ln PV at V is equals to V, another one is RT ln PV at V is equals to infinity. So, there is a minus symbol here. So, the limits lower limit is getting a plus symbol here, and then upper limit is getting a minus symbol here. Now, we have to find out what is ln PV at V is equals to infinity, this also we have to find out, and then what is ln f pi by p at V is equals to infinity, that also we have to find out, that then it is straightforward. So, the same equation I have written here once again. Now, RT ln PV at V is equals to infinity, at V is equals to infinity means what? It is ideal gas behavior. For the ideal gases, P capital V is nothing but nRT. So, that I can write is as RT ln NT-RT, because as V tends to infinity, P capital V is nothing but NT-RT, that is ideal gas obeys. One thing is clear. Then as V tends to infinity, we know that it is ideal gas behavior. So, for the ideal gas behavior, we know that the fugacity coefficient has to be 1, that is f I by yip has to be 1. That means at V tends to infinity or P tends to 0, f pi by P should be equals to yi, right, because at V tends to infinity or P tends to 0, the system reduces to the ideal gas behavior, and then for ideal gas behavior fugacity coefficient is 1. So, that is f I by yip is 1, that means f I by P is yi. So, that is RT ln f I by P at V is equals to infinity is nothing but RT ln yi. So, here we can substitute ln yi, and then here we can substitute ln NT RT. Then what we have here, RT ln f I by yip we will get left hand side. So, that is RT ln phi, and then right hand side I am just writing dou p by dou ni as a first term minus RT by V as a second term. So, that is the reason this minus is coming here, and then these two terms if you substitute here NT RT, then we can write RT ln PV by NT RT. So, this is nothing but RT and PV by NT RT is nothing but P small v by RT, that is nothing but Z. Okay. Now, this here here what I am doing, in order to remove this minus symbol, the integration limits I am changing certain v to v is equals to infinity, reversing the lower and upper limits I am reversing, right. So, then that minus is gone. Okay. This is PV by RT. So, that means I can have in place of PV by RT ln Z. Z is nothing but compressibility factor of the mixture. So, that means RT ln Phi is equals to RT ln Fi by Yip is equals to integral V to infinity dou P by dou Ni minus RT by V dV minus RT ln Z is the expression for a so called Figasty coefficient of that particular component in the mixture, right. And then here we have pressure explicit form, and then T and V independent variables. Out of these two, T we are keeping the constant, and then N components also, the composition also constant we are keeping. That means effect of V we can find out. If there is a change in V, how this Phi is changing, that is what we can get from by simply integrating this equation and simplifying it. So, Z is the compressibility factor of the mixture. So, equation 53 gives the Figasty of component I in terms of independent variables V and T, whereas equation 14 that we derived in the previous lecture, that gives the Figasty in terms of independent variables P and T. Here effect of volume we can find out, in the previous one we can find out effect of pressure on the Figasty at constant temperature and composition, right. So, in the previous one we have Vi bar, here we have dou P by dou Ni. Vi bar is partial molar volume, but dou P by dou Ni is not partial pressure. So, for a pure component I, how to get this Figasty of that pure component I if the equation of state is given in a is available in a pressure explicit form. So, that part we will see now. For a pure component I, Yi is equals to 1 and Ni is equals to Nt, because there is only one single component, pure component in a pure form. So, that then equation of state will be having the form P as function of temperature, volume and Ni, number of that pure component I. Then we know that dou P by dou Ni at constant V multiplied by dou Ni by dou V at constant P and multiplied by dou V by dou P at constant Ni is equals to minus 1 from the principles of differentiation. Then this we can write dou P by dou Ni is equals to minus dou V by dou Ni at constant P, dou P by dou V at constant Ni. This is what we can know. And then for pure component we know that this dou V by dou Ni is nothing but V by Ni, that is molar volume itself. That is partial molar volume is equals to the molar volume of that pure component, because the component is pure, and then molar volume we can write it as total volume by the number of moles, that is capital V by Ni. And then it is here in this case now dou P by dou Ni is minus V by Ni, dou P by dou V at constant Ni. Now what we do? We add and then subtract P by Ni from this expression, and then we rearrange this part P by Ni plus V by Ni dou P by dou V, that we can write it as dou by dou V of PV. This is what we can write, right. Then we need actually dou P by dou Ni in Figasty expression, integral of dou P by dou Ni we need. So, that now we try to do. So, dou P by dou Ni here we have seen it for pure component is nothing but P by Ni minus 1 by Ni dou by dou V PV. Okay. So, this is now if you integrate this part from V is equals to some finite V to V is equals to infinity, then we have integral P by Ni dV minus 1 by Ni dou by dou V of PV dV. So, now here this dV dV if you cancel out, then we can have a integral of dPV. Integral of dPV is nothing but PV, and then at V is equals to V, we will be having PV is equals to PV itself as a lower limits, because now limits also we have to change. Here in the previous case lower it is with respect to change in volume. So, lower limit was V. Now, it is with respect to PV. So, when V is equals to V, then PV should be PV, and then when V is equals to infinity, then PV should be same as a ideal gas behavior, that is Ni RT or NT RT. So, that is what we have written. So, upper limit will become Ni RT here in this case, if the integration, if we are doing the integration with respect to PV. Okay. So, then when you integrate this part, we will be having PV and then upper limit NiRT, lower limit PV. So, NiRT minus PV and then this divided by Ni is as it is. Whereas, the other part, this part we cannot do the integration, because what is that P we do not know, we are developing a kind of generalized expression. Okay. So, now integral dou P by dou Ni, we are having it as integral P by Ni dV minus NiRT minus PV by Ni, right. So, now here we know this, if I write this one, RT minus RT plus PV we will be getting, because capital V by Ni is nothing but molar volume. So, plus PV now here. So, PV minus RT is nothing but RT multiplied by Z minus 1. So, PV minus RT, if you take RT as common, then we have PV by RT minus 1. So, PV by RT is nothing but Z. So, that is RT Z minus 1. So, this expression we will be substituting in place of integral dou P by dou Ni in equation number 53 that we have derived. So, equation number 53 is this one. So, in place of dou P by dou Ni, we will be writing integral P by Ni plus RT Z minus 1, that is what we are going to write. So, that is nothing but this one. In place of integral dou P by dou Ni dV, we will be writing integral P by Ni dV plus RT Z minus 1, then we will be having this expression. So, integral P by Ni and then integral RT by V we are writing together, whereas RT Z minus 1 we have written separately, because it is not under integration. So, this is the expression for a fugacity of pure component I if the equation of state is available in a pressure explicit form. Okay. So, if the equation of state is available as a kind of pressure explicit form for pure component I, then if you wanted to measure the fugacity of that pure component I, you have to use this expression. So, now what we understood from equations 40 to 46 and 53 will enable us to estimate all thermodynamic properties relative to the properties of ideal gas at 1 bar and at constant temperature and composition, provided that we have information on volumetric behavior in the form of pressure explicit form, like P is function of temperature, volume and composition as given here, right. For a given equation of state, the associate expression for the compressibility factor PV by RT can also be written as a P by rho RT as well. So, that is we are writing here. Okay. Now, if someone wanted to write an expression for fugacity in terms of Helmholtz energy, then reduced molar residual Helmholtz energy A tilde can be written as AR. AR stands for reduced Helmholtz energy. Reduced Helmholtz energy is nothing but the Helmholtz energy at the realistic conditions minus Helmholtz energy at the ideal conditions. Okay. So, then A tilde can be written in terms of compressibility factor as integral 0 to rho Z minus 1 by rho d rho. Residual means the quality is defined relative to a mixture of ideal gases at the same rho, T and N as those of mixture of the interest. So, then associate expression for the fugacity coefficient of component I becomes ln phi I is equals to dou by dou Ni Nt A tilde plus Z minus 1 minus ln Z. Actually, this expression is nothing but the same thing whatever we have seen that equation number 53. That only thing that in place of this one we will be getting integral dou P by dou Ni minus RT by V dV. This is what we will get if you simplify this expression back in terms of a measurable property like pressure, volume, temperature, etc. Okay. But anyway, we are not doing that one because we need one expression that we already having it. So, that is more useful and explicit because it is in measurable pressure, temperature and volume and composition form. Here in this expression dou by dou ni of nt a tilde is given by this expression, whereas d by dxi is nothing but a differentiation with respect to xi while keeping all other xj as constant. Okay. The references for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnich et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, Introduction to Chemical Engineering Thermodynamics by Smith et al. Thank you.